4 plus 2 is 6, 6 on 2 is 3t, 4 minus 2 is 2 upon 2 is 3. So we have cos. Similarly, this is in the form of sin A minus sin B. What is sin A minus sin B? It is sin A minus sin B is 2 times of sin A minus B on 2 cos A plus B on 2. Now what is A minus B? 4t minus 2t, that is 2t. 2 on 2 is t. And 4t plus 2t is 6t on 2 is 2. So we have cos t. So we find that we can cancel this cos t. And we have the answer. It is A on, that is finally it is expressed as cos of pi on 3, which is nothing but A on 2. Now, this question, the same question, why I have taken up this form, why I did not go in for the value of dy on dt at t equal to, this is another thing that you need to see. I did not put the value here and then evaluate, because it might happen that you might get this expression, like if suppose my question had been this way, at pi on 6, instead of pi on 6, I am asking you to find it at pi on 6. At pi on 6, what we find is, this is nothing but 2 times cos of pi on 6, this will 2 times of cos pi on 6, this will come out to be cos pi on 3 plus cos of 2 pi on 3. Now what is its value? What will its value be? This comes out to be 2a. This is what I am trying to tell you. Please be very playful about this. Do not substitute the value in this expression of dy on dt or dx on dt. Here we get cos pi on 3 happens to be 1 on 2, whereas cos 2 pi on 3 happens to be minus 1 on 2. So this gets cancelled and we get a 0. Likewise, exactly the same thing you see here also. This is minus of sin pi on 3 plus sin 2 pi on 3. So won't you find that this also is coming out to be 0? So in that case, what will the expression of dy on dx value be? Because you have already evaluated the value here. It takes the form of 0 and 0. So isn't it an indeterminate form? So please avoid this thing. Always substitute the value after the simplification of dy on dx. So this is a very important fact to explain the parametric representation or finding its derivative at some point. So please do avoid such type of expression, that is because we come across indeterminate form 0 on 0. So we see that there is a common factor, that is cancel. We cancel the common factor and then get the remaining expression. I suppose this part is very clear to all. So make sure that you do not evaluate the value at that instant itself. For every question, see here, this is another question. We have 3 sin t minus sin 3t by 3 cos t minus cos 3t. So on differentiating x with respect to t, we get the statement. Here itself I have combined it because we can always take t and have it in the form of cos a minus cos t. And cos a minus cos t, it's minus of 2 sin a plus b on 2 and sin a minus b on 2. So using that formula, you have a minus sign, 2 times t minus 3t. T minus 3t is minus 2. Upon 2, that gives you a minus. I have taken that minus and made this sign plus. So that's the reason why you see a plus here. And that's 2 sin t sin 2t, that is 3 plus 3t on 2. 4 on 2, that is 2. Similarly, for dy on dx, it's minus 3 sin t plus 3 sin 3. So we can always take the common factor 3 and have the expression sin a minus sin b, as I said in the previous expression. It is sin t. So we go in for dy on dx, and here we find that yes, we still have a common factor. So we cancel the common factor and put the value of x as pi on 6. And that will come out to be cot 2 pi on 6. So you might come across again for some particular point where suppose you have it as dy on dx at t equal to pi on 2 to pi, assume that it is for pi. So in that case, Won't sin pi be a 0 and sin pi be a 0? That is again, won't it take the form 0 on 0? To not avoid this. So that is the reason why I say avoid this form, because that's very important to see. We do not substitute the value of t here. I have not written, this is wrong way of writing t equal to pi on 6. We don't put the value, we'll put only at the end. So have I made this point very clear? This is one of the important factor for parametric differentiation. So that's regarding the first order. Now we move on to the higher order derivative. That is, parametric function can be differentiated more than once. Now how do we take up the derivative? The first thing is we go in for dy on dx. That's okay. We got the value of y, derivative of y with respect to x. Maybe in terms of t or may not be. That's up to us. That is, if we can convert in terms of x and y, fine. Otherwise, we carry on this. Now, to take up the higher derivative, what we do is we differentiate again. So how do we take up? We take up the operator dtx of on both the sides, and on the left hand side, the derivative of dy on dx is written as d2y upon dx squared. So that's the derivative, second derivative of dy. That is, once again we are differentiating dy on dx. That gives us d2y upon dx squared. And on the right side, it's a function in t. So let us first differentiate that function of t. So that gives us f prime t. Then we take up the chain rule. That is, t has to be differentiated with respect to x. So we have dt on dx. And we already have the value of dt on dx. Bring that here. So that gives us the next derivative. That is second derivative of that expression. For that I have taken this example. See, x is equal to 2 cos theta minus cos 2 theta. Y is equal to 2 sin theta minus sin 2 theta. So respectively, we take up the derivative of x with respect to theta, y with respect to theta. On taking up, we find this is the expression that we get, and dy on dx comes out to be this form. So here, I have again used the simplification. We have cos A minus cos B. Wherever possible, as far as possible, always try to simplify the expression. That will always help us to avoid doing mistakes. So this is cancel, the common gets cancelled, and you have it as sine upon, this is, I think I made a mistake, this is sine upon cos, this will come out to be a tan 3 theta on 2. There is a mistake in this expression. 2 sine theta on 2 gets cancelled, it is sine upon cos, gives us tan 3 theta. So therefore, it is a derivative of tan 3 theta on 2 which has to be taken up further. So we again apply the operator. Please do correct this mistake. This can be corrected. This expression can be corrected. We can do the correction later. So it is differentiated with respect to x. The left hand side is the y on dx squared, and the right side is the derivative of tan. Derivative of tan is, this is a wrong statement. I am writing the correct statement. Derivative of tan is 6 square 3 theta on 2. So we can always it's 6 square 3 theta on 2. Then the derivative of is 6 square 3 theta on 2. Then the derivative of 3 theta on 2, that is 3 on 2 d dx. We have to differentiate theta with respect to x. So we bring that term here and do the necessary correction here. We have this as 3 on 2 6 square theta on 2 multiplied by, now what we have as dx on d theta, it is this fact. We have 2 times, it will be in the reciprocal. So let me write that. It's 2 times sin 2 theta minus sin theta. So if there is a need for simplification, we'll go for the simplification. Otherwise, we'll keep this as the answer. Let this be the answer. Don't touch this expression further. Okay? So what mistake I have made, please do the correction. This is wrong. This has been changed. This is to be changed to tan. Another variation. Another variation that I have taken up in this is The first question is same, finding the second derivative of dy on, next derivative of dy on dx. That is second derivative of y with respect to x. This is second derivative of y with respect to x. So we will have to get dy on dx, and from there we go in for differentiating once again, we get d2y on dx square. But the next question that I have written is d2x on dy square. What does that say? It is little different. d2x upon dy square, which is the next derivative of dx on dy. And with respect to what? It is with respect to y. So it is x second derivative of x with respect to y. So please make this clear. It is the second derivative of x with respect to y, which is the first derivative of dx with dx on dy with respect to y. So we apply the operator. Accordingly, the operator is to be applied. It is d dy on both sides. It's d dy. We have applied the operator dy. So that gives us dx on dy square written way. The right side, we first have an expression in terms of theta. So we differentiate it with to theta. So वो बन जाएगा minus cosec square theta. Then the derivative. Further, what we have the derivative of theta, which is d theta on dx. d theta on dy with respect to dy. तो जो d theta on dy वाला टर्म है उसको ले आएंगे. That is 2 e to the index that is taken up as a reciprocal. उसको लेकर आए. Again, इसका simplification की जरूरत है. We can go into a simplification. The simplification दिख रहा है. This is sin cos square theta and sin theta that makes it cos theta. Otherwise, छोड़ दो इसी form. Do not try to simplify unless until the question demands for it. Is that clear to you? Now here, next variation. पहला variation तो मैंने दिया है d2x upon dy square. That means it's the second derivative. This is the second derivative of x with respect to y. We have d2x on dy square. So first we go for dx on dy first. dy on dx निकालते हैं as usual. dy on dx करते हैं निकालने के लिए dy on dx with the simplification. देखो x is equal to e to the index t plus e to the index minus t. तो डेरिवेटिव क्या हो जाएगा? e to the index t. The minus is of the index minus t. The minus यहाँ है. And here it was a minus. Y was with minus sign, but here minus का derivative से plus हो गया है. So when you take dy on dx, you find that this is the expression that you get. अब इसको हम x and y में convert कर सकते हैं. So we always get the value of y dy on dx in terms of x. So second derivative निकालना easy हो गया अपने लिए with respect to x और y, whatever it is, हमें easy हो जाएगा. So we all have मैंने तो यहाँ पे quotient tool use किया है. Quotient tool क्या है? f1 upon f2 derivative. It is denominator multiplied by derivative of numerator. Y को differentiate with respect to y. क्या आएगा आंसर? 1 minus y times now x की derivative with respect to that is dx on dy upon derivative upon square of the denominator. So इसका simplification is converted to this. The second part है. Second part is to find another important thing that we have. That is a variation that we have in the parametric form. That is, you have to find 2y into t on dy square. तो पहले तो हमें ये समझना है कि ये क्या चीज है. What is d2t upon dy square? d2t upon dy square is actually the second next derivative of dt on dy. So it is the next derivative of dt on dy. So dt on dy का differentiate first अपने को dt on dy चाहिए. We already have that expression dt on dy. So we differentiate both sides now with respect to y. So what we have is on dy, e to the index is to be differentiated. यहाँ पे multiplied by we have dt. This is dt upon dy. So this is now an expression in terms of t. So we have to use we have multiplied by respect to t. Here e upon dy has to be that's another and here. It will introduce this term upon dy from the previous expression. यहाँ से लेकर आएंगे and we'll complete it. It is minus 2 e to the index minus it may differentiate the side t4. We have to differentiate with respect to y. तो हमने बाद में second time पे लिखना पड़ेगा. Is that clear? तो complete करें. So we have these variations. Variations के ऊपर आपको बहुत ध्यान देना है कि with respect to what has been asked, due to x upon dy square है, due to y upon d theta square है. So that's very important. आपको यहाँ पे d2 y upon d theta square दिया है, and that to at this point is further extension of this question. That is the second derivative नहीं है. When you have to find the value of the expression at the given point, find the value of the derivative of d2, that is y with respect to theta, that is y which we differentiated twice. Differentiate y with respect to theta twice. पहले हमने dx और dy निकाला, dy on d theta निकाल दिया, and then not dx or dy because I wanted the second derivative of x with respect to y. This case I have applied y on both sides. So we have d theta on dy. तो टर्म को लेकर आना पड़ेगा यहाँ से आपको. Okay, so that is 1 upon d sin theta. So that direction. This is 1 upon d sin theta. So this is d theta on dy. That is 1 upon d sin theta. If you require further explanation, you can go with it. So that's what we have for the second derivative of different types of expressions. Now, what is the application that we have? Now, this part I said, इसको मैं देख लेती हूँ यहाँ पे. इसको देख लेते हैं. This q y on d square means it's the derivative of dy on d theta. Second derivative of y on d theta. ये जो expression है, इसको आप differentiate करके एक बार और that will give us the next derivative of y with respect to theta. Now, the next thing that we have is another very important thing, that is application of this parametric form. The application of this question, what is it? You'll be getting a question like find the derivative of log of sin x with respect to cos x. So here we can make use of the parametric form. We can always go to a situation. We can take y as log sin x and t as cos. So what does the question say? Differentiate log, differentiate y with respect to t. So you are supposed to find y on t. The expression जो है now, it is connecting y and t, not x. ये ध्यान रखना है because this is an application of the parametric form. So पहले तो we find y on d, which procedure remains as go for y with respect to x. We have the derivative of log sin x cos x upon sin x, that is cos x. Then the derivative of with respect to x, that is minus y. So what is there for dy on d? It is dy on d and dx to dt. It is dy on dt, dx multiplied by dx on dt, that is x differentiated with respect to t. That gives us minus 1 upon sin. This is the final answer. We have another question based on this, that is differentiate this expression, that is sin inverse x upon 1 plus x square with respect to tan inverse x. So how complicated the expression reads, but it is not that complicated. We can also go in for the parametric form, reduce it, derive y as this and t as tan inverse x. इससे क्या हो जाएगा? We can always put the value. I have said that we can place the expression y and t or y and x related. What I have done is I have x as इससे we get an identity 2 tan t upon 1 plus tan square t is nothing but sin 2t. Therefore, we have sin into 2 which is 2t. We have as 2. It is just a 2 here. Derivative of t with respect to x, it is just a 2. So we have the answer. So how easily we could get the answer. Likewise, there is another question. X to the index sin inverse x with respect to cos inverse x. So however complicated the expression may be, it should not be a problem for you all. We can always go in for the differentiation by making use of a parameter. So we have taken care of this. It made it looking like a linear expression. Fine, doesn't make any difference. Now, what I'm trying to discuss now is one very important question of the textbook, which is saying that we have an expression x minus a whole square plus y minus b whole square is equal to b square. You have to show that the 1 plus dy on dx, that is the first derivative square, upon the second derivative, just a check. The second derivative, that is y2 square raised to the numerator is going to the index. This is independent of a and independent of a and with a very important question. How to take this?
Right. Veena Prakashji here, I would
Fast.
like to remind you, we just have another 2 to 3 minutes left for this session to be ended. I would like
Just a
you
minute,
to
ma'am. I'll just
conclude.
immediately it up.
Yeah.
I'll just take one more step.
Sure.
Now, if you take this expression in terms of parametric form, that is, you have x is equal to a plus c cos theta. This is an equation of a circle. If you see it carefully, you know that it's an equation of a circle with center a and b. So if you take a as this, b as b, y as b plus c sin theta, you find that the expression gets converted to this form. So then in that case, finding dy on dx is easier because we know that derivative of x with respect to theta is minus sin theta and y with respect to theta is cos theta. So it takes the form of minus cot theta where a and b is a constant, they can cancel, c also will cancel. So very easily we could get the first derivative and differentiating it further we get dy on dx square is minus derivative of cot theta is plus square theta with minus it plus d theta upon dx. And d theta upon dx means it's to be differentiated, that is minus 1 upon c sin theta. So if you put the value in this expression, you have 1 plus but first derivative is nothing but minus cot theta, that gives you 1 plus cot square theta to the index equal to divided by the second derivative. Just calculate as cosec cube theta upon c, which is multiplied by c. So the whole expression that you read here is nothing but cosec cube theta, which gets cancelled. Finally, we have a term which is going to be independent of a and b. So that's what I want to tell you. This is a very, very important question of the miscellaneous exercise. You can always expect this question. Okay, thank you. Ma'am, any more questions?
Veena ji, thank you. I guess the session was indeed useful for mathematics students of class 12th. And thank you for joining us today. It was wonderful to have you.
Thank you, dear students. All the best. And any doubt you have, please do mail me. I'll be always there to help you out. Thanks a lot. Namaskar.
And viewers, remain connected to NCERT's resource material on PM eVidya. Thank you. Namaskar.